Our third speaker is Sergio Marchese of OneSpin Solutions. He's the technical marketing manager. The topic of his talk is hardware safety metrics for ISO 262. Sergio has 18 years experience in hardware design, constrained random simulation, formal verification and design for test. He has built and managed state-of-the-art teams, successfully achieving formal sign-off on complex designs. Before taking the role of technical marketing manager at OneSpin, he served at Huawei, leading formal verification for an ARM CPU and consumer SoCs. And he's located in Spain today. So over to you, please, Sergio.
Hi, everyone. So, yeah, another presentation on safety, and in particular on hardware safety metrics for ISO 26262 compliance. Okay, so introduction to functional safety. I think you already heard quite a lot about this. So the objective of functional safety is the freedom from unacceptable risk of physical injuries and so on and so forth. And as Alex said in the first presentation, we have two main classes of failures that are considered in the standard, which are systematic failures and random failures. And in this presentation, we will focus on random failures, and in particular the need to safeguard safety critical hardware from random faults that will occur during the operation of the circuit while you are driving your car. So safety mechanisms are used in order to prevent faults from leading to failures, and what they do, they detect and faults, and they potentially correct their effect, and ultimately they have to prevent or control hardware failures. We can have different type of hardware faults, and we distinguish typically between permanent faults that are, let's say, faults that cause permanent damage in the circuit, for example, a single event latch up, or we can have transient fault, for example, single event upset, which could be a bit flip in the memory due to some alpha particle or some other physical phenomenon. And this will not cause a permanent damage of the hardware, but of course can cause failures. And we have software-based safety mechanisms that detect hardware faults, and we can have hardware-based safety mechanisms. And we will really focus in this presentation on the hardware side. And typically the safety mechanism will protect some safety-related function, and it might, correct, for example, the output, and it will raise an alarm if it detects a fault. And actually, in the general case, the alarm could be even optional. Of course, if the alarm is optional, if the alarm is not present, then the safety mechanism would have to correct the effects of the fault and make sure the output of our hardware is correct. So in these pictures that we will see now a lot, and we are going to dig into fault classification and the various type of faults that we need to consider, and we will have the alarm signal, and in green we really indicate when the alarm is inactive, so the safety mechanism didn't detect any problem, or when it's active in red. And then when the alarm is active, then when the alarm is inactive, so the safety mechanism is saying, there is no problem that I detect, then we indicate with green if we get the correct output, or in red if we get the wrong output, so we actually have a failure of our hardware, so to speak. So let's see what type of faults we need to consider when we do ISO 262 safety analysis. So one category of faults are safe faults. So these are faults that cannot cause failures. So for example, here we have a safety-related function, we have a fault, but for some reason, maybe there is no way to activate these faults, or there is no way that these faults will propagate to the output. And for example, this could be, a very trivial example, is a stuck at zero fault on a net that is already tied low. This will not change the functionality, so it will not cause any problem. And the interesting thing here is that on one side, safe faults are important. You know, we want to identify safe faults to improve our metrics. And also, it's interesting to note that actually there can be a lot of safe faults in our hardware. And you know, this is a simple example, but there are many more complex situations. So let's move to the next interesting category, single point fault. Single point fault are fault on the safety related function that can affect the output. So typically we actually consider single point fault on functions that are unprotected. So if you see here, there is no safety mechanism protecting this function. There is a fault. This fault propagates to the output. We get the wrong output. And so this is actually a bad fault, and we call this single point fault. Another bad fault, another bad guy, is the residual faults. In this case, we have again our safety related function. We have a fault in this function. And just a side question. Do you see my pointers, the laser pointer, when I use it?
Yes, we do, thank you.
Okay, thank you. I was wondering. Okay, so we have a fault in the safety-related function. We have a safety mechanism that is protecting this function. So here we have the unprotected output, and here we have the protected output from the safety mechanism. Unfortunately, in this specific situation, the safety mechanism doesn't report any problem. The alarm is green, but the fault corrupts the functionality of the design, and we get the wrong output. The protected output is red. So we have the situation where the fault is not detected by the safety mechanism, make its way to the output and cause, let's say, a failure. And in this case, we call this residual fault. So this is the nomenclature from the ISO 26262 standard. Now, so far we have considered the situation where we have a single fault, but we can also have multi-point faults, and we see now why these are also interesting. I mean, one could say it's already a pain to consider single faults. Do I also need to consider when there are multiple faults at the same time? Actually, you do. And so let's see more about multi-point faults. So a multi-point fault by itself is not a bad guy. So because a multi-point fault is a fault that on its own will not cause any failure. For example, here we have a fault in the safety function. This fault makes its way to the unprotected output, so this is red. But the safety mechanism is good enough in this case. It detects the faults and raises an alarm. Maybe it also corrects the faults and we get the correct output. But the important thing really here is that the safety mechanism is detecting this, raises the alarm. And so this is, let's say, not a bad fault on its own, and we call this multi-point fault. Of course, the problem with multi-point fault is that while this guy on his own didn't cause any problem, along with some other fault, for example, let's assume I have a fault in the safety function, I have a fault in the safety mechanism. These two guys together cause that, in this case, you know, I get no alarm from the safety mechanism. So the safety mechanism thinks it's all okay, no problem, but actually I get the wrong output. output is red, and so I get a failure, and this is called multi-point failure. So the interesting thing here is that the multi-point fault doesn't cause a failure, but two multi-point faults together can cause a failure. Now, a very important category, which we already mentioned, we've heard in some previous presentation, is that latent fault. Latent fault is a special class of multi-point fault, and let's dig more into latent fault. So a latent fault is a fault that, for example, let's consider this case, a latent fault in the safety mechanism. The fault does not cause any alarm to be raised, so alarm is green. The fault does not cause any wrong output, so it doesn't affect the safety-related function. But this fault is important to consider, because if you think you have a permanent fault in the safety mechanism, this fault is actually potentially compromising the protection of a large chunk of safety function. And for example, you might have a safety mechanism in the hardware in your car. After 1 year, something goes wrong, and this fault stay here. It doesn't cause any problem, but it's there. And later on, if you get an additional fault in the safety-related function, as we saw before, these two can cause a problem. So maybe you get a latent fault in the safety mechanism that breaks it, a permanent fault, and maybe after 2 years' time, suddenly you get a bit flip in the safety-related function, and right when you would need the safety mechanism to do its job, actually the safety mechanism is broken, and you didn't know about it, nobody warned you, you didn't get any indication of it, and suddenly you run into problems. So yeah, so this is, let's say, the typical scenario, I would say, of latent fault, where you have a latent fault into the safety mechanism, a permanent fault in the safety mechanism that together with some other fault can cause problems. But another interesting thing to consider is actually you could have, in some circumstances, latent fault in the safety-related function. So let's consider the scenario where you have a fault in the safety function. The safety mechanism detects it, corrects it, so you get the right output, but either you have no alarm in the safety mechanism, or for whatever reason, the safety mechanism is not raising the alarm. So in this case, you are in the situation where there is a fault here. Let's say this is a permanent fault, and you don't see anything about it because the safety mechanism is correcting it, and there is no indication, because of the way the safety mechanism is, or because of the way it is configured, whatever, there is no indication that there is a fault here. And this is a permanent fault, and actually, it's, if you think about it, is a latent fault, because this fault on its own is not causing any problem. But suddenly, at some point, you get maybe another fault, let's say in the safety mechanism again, and suddenly you have a problem. So it makes sense. Basically, I guess the goal here is to say it makes sense for the standard to consider latent fault. And in general, it makes sense to consider multi-point fault. Typically, the standards focus on what it calls dual point faults. So when you have two multi-point faults causing a failure, but in some cases, you might have to consider multi-point faults of order 3, where you have to consider what happens if you have 3 faults at the same time. In some cases, that's also necessary. Okay, so the single point fault metric is one of the important metrics in the standard that reflects the effectiveness of the safety mechanism to protect from individual faults, single point faults, and residual faults. If you have many faults, you can expect higher single point fault metric. If you have effective safety mechanism, you are going to have a few residual faults, and you have higher metric. And of course, on the other hand, if you have unprotected function, you are likely to have many single point faults, and this will lower your SPFM. So this is the formula from the standard where lambda is the failure rate. And similarly for latent fault metric, the latent fault metric reflects the effectiveness of the safety architecture to protect from multi-point faults. And here, you know, for example, if you have many detected multi-point faults, you're going to have higher LFM. Yeah, so I think this metric, the important point here, that this metric is important to account for the fact that you can have latent fault and you want to assess how good your safety architecture is with respect to this type of faults. So if we look at the standard, we're really focused this presentation on one section of part 5 of the standard, evaluation of the hardware architectural metrics. These metrics give evidence that the hardware safety architecture is adequate to prevent control random failures, and it is adequate, of course, depending to the target safety integrity level, which we already had before. And for example, for ASIL-D, there is a very high target for SPFM and fairly high as well for latent fault metric. Just one note, because we have talked a bit about permanent transient fault, that some of these metrics may need to be computed separately for the different fault types. And there will be another interesting part on the PMHF, probability metric of random hardware failures, which is really this bit of the standard, but for time reason, I'm not going to go into that. So in summary, we have seen the fault classification. We have safe faults, single point and residual faults, multi-point faults, detected and latent one. We have seen the key metrics from ISO 26262, SPFM and LFM, which are really important to provide evidence that the hardware safety architecture is adequate. And from one spin side, I'm not going to tell much, you know, you can contact us if you want to know what we provide, but just to mention a few things, we have unique and automated solution for fault classification at different abstraction levels that really brings not only a lot of automation for your FMEDA analysis, failure mode, effects and diagnostic analysis, but also, you know, they reduce reliance on expert judgment. Some of you who have gone through ISO 26262 project know that this may take a lot of time. We integrate with third-party tools. And another important point is that through this analysis that we do, you can minimize your fault simulation, which is time-consuming. And here, you know, I'm not just talking about formal analysis, identifying safe faults or collapsing faults. There is much more than that. And this is proven in both established and new suppliers of automotive hardware. This is a quote from Carl Ray, who recently developed technology, many-core technology for autonomous vehicles. And one last slide, talking about ISO 262 certification of tools that you will need if you when you use tools for ISO 26262 analysis. And we have done our certification through TÜV-SÜD, which is quite established certification provider. And I think I don't have time to talk about this, but if you look at this stamp that we got, it's quite different from other stamps that you may see from competitors. And there are reasons for this. In particular, we don't just certify documentation that we provide, but we went through also an assessment of our overall development process. And also we got a one-spin factory audit and inspection. So a bunch of things which enable us to reach a level of qualification which is much deeper and enables much easier qualification flow for our customers. If you want to know more, you can go to onespin.com/TÜV.
Okay, thanks, Sergio.
Thank you.
Unfortunately, we've got a couple of questions, but we've run out of time for those questions now. So thanks for the presentation. And yeah, very interesting analysis of the different types of faults, which people may not realize there's different types of faults which you need to detect. Okay, so we're going to move on to our final speaker now. Just quickly, thank you, Sergio, before we move on. Thanks, Sergio.
Thank you.